Hello, and welcome to week 4, lecture 1. Today we're going to talk about tension and normal force. This is covering chapter 5-2. We're going to introduce tension and then do sample problem 5-1. And then we will introduce normal force and do sample problems 5-4 and 5-7. So, tension. And here we have a worker applying a pulling force to the string or rope that is attached to this crate here. And it's causing the crate to accelerate. And we want to note that the worker isn't applying the force directly to the crate. They're instead applying a force to the string, which applies a force to the crate. And we call this force that is applied via a rope or a string tension. So we can look at the partial free body diagrams for the string and for the crate. And from the size of the vectors, we can see that the pulling force of the worker is equal in magnitude to the tension force in the rope. And so here's the string or rope and then the free body diagram for the crate. And remember also, you can kind of think of tension as a third law action-reaction pair because the things that are attached to it or being pulled by it experience the force equally but in opposite directions. So like you can think of this as like a portion of the string, and so a portion of the string feels the worker's pulling force and tension in the other direction along the rest of the string, and the crate feels that same tension but in the opposite direction. So now we're going to do a sample problem with this. 5-1, a block of mass M, M equals 15 kilograms, is hanging from 3 strings. What are the tensions in the 3 strings? Okay, so I have the picture on here to help us out. And what we're going to do is draw 2 free body diagrams. So we're going to draw a free body diagram for the knot and for the block, okay? So let's do the knot first. F plus X, Y. Okay, so we have, oh, that was the eraser. We have the tension B. We have the tension A. Okay, and then we have the tension B. Before I worry about the angles, I'm just going to add the free body diagram for the block, which is its weight pointing down, and then tension C pointing up. And these are all vectors. Okay, but we also need the angles here because we see that we have forces acting in X and Y. So I'm giving us a horizontal plane here on the diagram. And this theta B is what we'll call it, and this one we'll call theta A. And just from geometry, these are actually equal to the angles they gave us there, where theta A is 30 degrees and theta B is 45 degrees. And just really briefly, I don't want us to get off track, but I also don't want people to get stuck on this. You can see this from the relationship between angles in a triangle. Because these are right triangles, this angle here is 90 degrees for both of them. And then this angle is theta A, or this 30 degrees subtracted from 90. And that also is what this angle is. So please let me know if you would like a more detailed explanation of that. But in general, that's what the angle is for those. So I'm going to put that here also. theta B, theta A, and then I'm also going to put my X and Y component. So the Y component of B and X, and for A and Y and X. Cool. So now we have equations for forces. We should, or sorry, getting ahead of myself. We have free body diagrams, so we should get equations for forces now. Maybe before we do that, we'll just quickly write down the equations for tension for the different components of the tension. So let's see, TAY, this angle is, or this one is opposite of the angle here. So that's going to be sine, TA sine theta A. And then that means X is going to be cosine TA cosine theta A. And then we can see that B is actually the same thing too, but it's that angle B. TB sine theta B and dx TB cosine theta B. Okay, now let's make those force equations. And remember, again, this is just reading from our free body diagram. So let's start. Oh, I didn't label these. This is the knot, and this is the block. And we're going to start with the knot, and we will start, it doesn't really matter. So we'll just start in the X direction. Sum of forces in X. One thing to note, so you can kind of do this part two ways. You could just write mass times acceleration. I mean, we don't know the mass of the knot, so it's not entirely helpful. And then later determine that it is 0, but none of this stuff is moving. There's no indication that it's moving. Otherwise, the problem would have told us. So we can just say the net force in this situation is 0, both in X and Y. So in X, we have the X component of tension B in the positive direction, and then the X component of tension A in the negative direction. I'm just going to write them this way instead of the equation right now. Okay, let's do the Y direction. Again, net force is 0. So in the Y direction, we have the Y components of the forces, or the tensions in the positive direction. So we'll just add those together. TBY. And then CC is subtracted from them. And then we have the block. So there's no X forces. I mean, we can still write it for completeness, but it's 0. But in the Y direction, net force is also 0, but there are individual forces. There is tension in C, and it is subtracted by the weight because tension in C is in the positive Y, weight is in the negative Y. And one thing we can do just really quickly, because this is such a simple equation, is if we add the weight to both sides, we see that the tension in C is just the weight of the block. And weight, remember, is due to the force of gravity. So the equation is mass times acceleration due to gravity. And so we can just calculate this really quick, get it out of the way. So 15 kilograms times 9.8 meters per second squared. Sorry, I'm like on the edge of the page there. And that is 147 newtons. So that's TC. That will come in handy. Now let's move back to the force equations for the knot. Let's see, let's just kind of see what we can do with these. So we have, for the X equation, we can again add tension A to both sides. And so then we have just that the x component of B is equal to the x component of A. That makes sense because those are the only forces in the x direction and we have no acceleration. So that's good. And maybe we'll plug in our equations here so we don't forget about them because I do that sometimes. Cosine theta A, and that equals, oh well, it's, no, I'll do it the right way. This side was B. CB cosine theta B and TA cosine theta A. Okay, and we can actually from this get a equation for the tension in rope B in terms of the tension in rope A. So we might as well do that because hence it will come in handy in a moment. TA cosine theta A. So that's just dividing cosine theta B on both sides. By the way, I didn't say that. Okay, that's cool, helpful relationship. And then we have this equation here. So maybe we'll just keep it as it is, but we'll write everything out. So we have TA sine theta A plus TB sine theta B. And I might just keep TC as TC for now, since we have a number for that we'll plug in a little bit. So now is where having this relationship comes in handy because we can plug this in for TB right here, and that gives us one thing we don't know, which is the tension in A. So we can solve for that. So let's do this. 0 equals TA sine theta A plus TA cosine theta A over cosine theta B times sine theta B minus TC. Okay, and one thing to note, just to kind of simplify the stuff we have, the sine over the cosine of the same angle is tangent, so it's like sine of theta B over cosine of theta B is tangent theta B. Just reduce the things we have to write down and calculate. So 0 equals TA, and I'm actually gonna skip a step here, sort of, and factor out TA from both of these. So in doing that, that's just sine theta here. But then the next term is just adding cosine theta A tangent of theta B minus TC. Okay, and then we can add TC to both sides and also divide this whole thing on both sides to give us tension in A by itself. So then we have TC divided by sine of theta A plus cosine of theta A tangent of theta B. Okay, now so TC we already found is 147 newtons. And this is a sine of 30 degrees plus cosine of 30 degrees. Let me double check that that's right. Yeah, that's it. And tangent of 45 degrees. And this gives us tension A of 108 newtons. Tension in A. And we have this equation here that has tension in B in terms of tension in A and the angles. So we can just also plug that in. And I ran running out of room, but I think I can fit it. Let's see. TB equals 108 newtons times cosine of 30 degrees divided by cosine of 45 degrees. And this is 132 newtons. So that is the tension in each of those ropes. And I'm just really quickly gonna summarize what we did because this is a little bit long. So we drew free body diagram of the knot and of the block. Part of why we did this is because there's these two other ropes that come off of the knot that the block isn't actually attached to like independently. So in order to find the tension in those ropes, we needed a free body diagram from there. So from our free body diagram, we generated our equations from, again, just reading it off the free body diagram. And then we saw we could solve right away for tension in rope C. It's just the weight of the block. And then we used these two equations and what we found for tension in C to solve for the other two tensions. Okay, let's go back to the slides real quick. Okay, so now we're going to talk about normal force. So we have a book resting on a table. And we know that the book has a force acting on it from the earth, the weight force. But if this book isn't accelerating through the table, there must be another force acting on it in the opposite direction. Otherwise, it would be experiencing acceleration in the y direction, since it has at least one force acting in that direction. So this force is applied by the table, and we call this normal force, the normal force. And normal here doesn't mean like the regular typical force. No, it means perpendicular. So it's the force that is perpendicular to the surface. And we can see it in the free body diagram. The weight force points straight down and the normal force points straight up, equal and opposite, because there is no acceleration happening. So there has to be zero net force. But these are not an action-reaction pair, because remember, the action-reaction pairs act on different objects. Both of these are acting on the book. So that's one reason. And it's true that they're both each independently part of an action-reaction pair. Like the weight force is this force due to gravity on the book from the earth. And the earth also experiences a force from the book. And then this is the normal force on the book from the table, and the table also experiences a normal force from the book. And the normal force is just a force, the force a surface needs to apply to prevent acceleration in that perpendicular direction. So if the book had more mass, the normal force would increase with the weight of the book. Or if someone pressed on the top of the book with some force, the normal force would also increase in relation to that added force. And if we kept adding more and more force, we would just end up getting to a point where the table could not handle the force anymore and it would break. And then there would be acceleration in the y direction. And in this situation here with just the book on the table, we only have two forces in our free body diagram, but in the one I just described where someone's like pushing on the book or something like that, there would be an additional force on our diagram, and it would also point down, and it would be like a pushing force or something like that. So the normal force would equal the weight force plus that pushing force. Okay. Now, we're going to do sample problem 5-4. A block of mass 18 kilograms is held in place by a string on a frictionless plane inclined at an angle of 27 degrees. Find the tension in the string and the normal force exerted on the block by the plane. Analyze the subsequent motion after the string is cut. Okay. And here's the figure from the textbook for this. So one thing we're going to do, which I think we've done, but more formally, we are going to draw a free body diagram on an incline this time. And this will be a complete free body diagram, not just a partial one. So, and actually before we do that, let me show you something. I'm going to just draw the weight force really quick so we can see this relationship here so that you see how we know these are the same angle. Okay, I will call this one theta 1 and this one theta 2. And this will be phi. And so we'll, this will be phi 1. I don't know if we need that one. And then this is 90. So the triangle, like the total angles, in if we added up all of those, is 180 degrees. So it's 90 plus theta 1 plus phi. Okay, but this is also 90 because those make a right angle. So 90 degrees equals theta 2 plus phi. And we can actually subtract this 90 on both sides, and we get 90 degrees equals theta 1 plus phi. So that tells us that theta 2 and theta 1 are equal. So just from geometry of the situation and trig, I guess, that's how we know how this incline angle is also the angle between the weight force and the negative y-axis. Okay. Now on to the actual problem. So positive x, this is positive y. And again, this is the theta of 27 degrees. And then I'm going to draw the weight force straight down. And this is also theta. Okay, and then the other forces acting. So we have tension up along the positive x-axis. And then we have normal force up on the positive y-axis. And then really quickly, our weight force in the y and in that. Now we can do our sum of forces. Sum of forces in x, and at this moment, nothing's moving. So the net force is 0. Well, it doesn't, there's no acceleration. That's the actual important thing. And so reading from our free body diagram, tension is in positive x, weight, x component of the weight is in the negative x. So that's what we end up with there. And sum of forces in the y, also 0. And we have the normal force minus the y component of the weight. Yep. So, and I forgot what they asked for. The tension and the normal force. Okay, cool. Well, that's easy because these equations give us that. If we add the weight force on both sides of both equations, we get equations for tension of the x component of the weight and equation for normal force, the y component of the weight. And the x component is in this case, so this is another thing to be careful about, pay attention to. Because we've tilted our axes, our angles work out differently this time. So the y component of the weight force is the one that is adjacent to the angle. So the x component is the one that is opposite. So that's the one with the sign. Y is cosine. Okay. So tension is the weight times sine of theta, which is, the mass is 18 kilograms. So 18 kilograms times 9.8 meters per second squared times sine of 27. And this is 80 newtons. And then we have the weight, or sorry, the normal force, which is the weight cosine of theta. That is, again, 18 kilograms, 9.8 meters per second squared, cosine of 27 degrees. And that is, just lost it, 157 newtons. So that's the normal force in the weight, normal force in the tension, sorry. And then it also asks for us to analyze the motion after the string is cut. And that is kind of a broad framing. But when we're dealing with forces, the thing we know we can find for the most part is acceleration. So that's what we're gonna assume they're asking for. Acceleration. So let's draw our free body diagram again, but this time there is not tension. I'm gonna change colors. There's still the weight force. This is still the angle. And there's still the normal force. And there's our X and Y components of the weight force. Weight Y, weight X. This part is still the same. So let's write our equations. Sum of forces in X. First of all, actually, let's start with Y. The object, we do not expect it to move through the plane. So we can say there is no acceleration in the Y direction, and we get the normal force minus weight in the Y direction. And then in X, here we will assume there is likely some negative acceleration because we defined this as positive X, this is positive Y. So this is negative X, and the force is only in that direction, like the forces in the X direction only act in the negative X direction. So that means our acceleration is going to be negative. And then this is negative WX. So you see how that just cancels those signs out, which is fine, but I think it's important to remember to include them initially because there will come a time where it's not going to neatly cancel out like that for you. And then you'll get the wrong answer because you forgot a sign. It happens a lot. So we have mass times acceleration equals mass times gravity times sine theta. So mass cancels out. That's cool, less calculating. And this tells us that our acceleration is just g sine theta. So 9.8 meters per second squared, sine of 27 degrees. And this is 4.45 meters per second squared. That's acceleration, but it's in the negative x direction or negative I hat. You can write it that way too. So that's important too, to come back to the fact that, okay, the direction is still negative. I'm not going to go back to the slides for this next example, since we're already in this. I forgot to erase leftovers. So this example is sample problem 5-7. A block of mass 9.5 kilograms slides on a frictionless plane inclined at an angle of 34 degrees. The block is attached by a string to a second block of mass 2.6 kilograms. The system is released from rest. Find the acceleration of the block and the tension in the string. So let's just start with our free body diagrams. When there's forces involved, it's always a good place to start. You could also just list your knowns and unknowns. Actually, we can do that really quickly because they didn't give us very much. Mass 1 is 9.5 kilograms, and mass 2 is 2.6 kilograms. The angle, 34 degrees, and the initial velocity for both is 0. Okay. So now, again, we're tilting our coordinate axes for the block on the incline. And one thing you can do in a situation like this where you have two different objects and therefore you're going to draw free body diagrams for both of them is that you get to choose the coordinate system for both. So this is for mass 1. For mass 2, we're just going to have a normal straight up and down one. So that's just, it's convenient to be able to do it that way. Okay, let's draw our free body diagram. Let's see, this is the same free body diagram as the previous example before we cut the string. Tension and normal force. Okay, and again, this is theta. And again, we'll just include our X and Y components. Then for the block that's hanging, it just has its weight force, weight 2, and the same tension force. And one thing to note is because we're finding the acceleration, we're assuming there is acceleration. And so what we want to do is just pick a direction of the motion. So I think it's most likely that the heavier block is gonna like pull the lighter block. So I'm gonna say our acceleration is in these directions. So this is negative x and this is positive y. And if we get that wrong, it's totally fine. Like the part you need to worry about is being consistent on if we say mass 1 is moving down, that means mass 2 is moving up. Don't assume that mass 2 is also moving down. That doesn't make sense. They can't be moving in opposite directions. So that's the part you have to keep in mind. And then if we're wrong, we'll just end up with a negative acceleration. And that tells us, oh, they are going the other way. So let's do our sum of forces. Sum of forces in x for 1. And so mass 1, this, remember, negative x, so negative acceleration. And we have tension minus the x component of the weight. And the y direction, this one, there's no acceleration for mass 1, because again, it's not going through the incline. And then we have the normal force minus the y component of the weight. Yeah. And then in for the other block, there is no force in the x direction and in the y direction. So again, mass 2 times acceleration. This time's positive because it's moving in the positive y direction. And our forces are tension minus weight 2. Okay, so we have our equations. Let's take a look at them. M1, negative M1 times acceleration tension equals the tension minus the weight in x. And then for this equation, I'm just going to add the weight in y to both sides so that we see the normal force is the weight in y. And finally, mass 2 acceleration equals tension minus weight 2. So we want to find both the acceleration and the tension. And we have, so it doesn't look like we'll need this equation because it doesn't ask for that normal force. But can use both of these equations and then we'll just quickly go through. We know these, we can calculate the weight since we know the mass and the acceleration due to gravity. And these are the things that we want, but we have 2 equations and 2 things we don't know, so we can solve. So the thing to do is just solve one of the equations for one of the things. So maybe we will solve this equation for the tension, and that's just adding the weight to both sides. So we get tension equals mass times acceleration plus the weight of object 2. Okay, and now we can plug this in for tension into that equation. So that way we get rid of tension in the equation and we can solve for acceleration. Negative m1 times acceleration, and then I'm going to plug in for tension here, which is mass 2 acceleration plus weight in 2, and then we're subtracting the x component of the weight for 1. I don't love my choice for this because there's annoying negative signs I don't like. How do we want to do it? I guess we will just subtract this on both sides and we will eventually divide both sides by -1. Get rid of the ugly negative sign. So you can write this as negative a m1 plus m2. So I just pulled the negative out and A out of both of those. And this one is weight 2 minus the x component of weight 1. So then I'm just going to divide both sides by negative m1 plus m2. Negative m1 plus m2 in parentheses. Gotta be careful. Okay, so the acceleration is equal to, and at this point, I'm going to plug in what these weights are because we're going to need to plug in numbers. So let's see, mass 2 times gravity minus mass 1 times gravity times sine of theta, right? Yes. And this whole thing is divided by negative m1 plus m2. So now we can plug in our numbers, and mass 2 is 2.6 kilograms times 9.8 meters per second squared minus 9.5 kilograms times 9.8 meters per second squared times sine of 34 degrees divided by negative 2.6 kilograms plus 9.5 kilograms. And we get an acceleration of 2.2 meters per second squared. So this is for mass 1, it's in the negative I hat direction, and for mass 2, it's in the positive j hat direction. And remember, this is just negative x and positive y. Okay, so we have the acceleration, but it also asks for the tension, but we solved an equation for the tension, so, and now we have the acceleration. We can just plug it in. Let's see, I'm going to try and fit it at the bottom just so that everything's on the same page. So tension equals mass 2 times acceleration plus mass 2 times gravity equals mass 2 is 2.6 kilograms times 2.2 meters per second squared plus 2.6 kilograms times 9.8 meters per second squared. And this gives us a tension of 31 newtons. Cool. So we have our acceleration and our tension in the rope. And just go over this one really quickly again too. So we have this situation with 2 blocks, one's on an incline, one's hanging, they're attached by a rope. We drew a free body diagram for both, and again, it's totally okay to kind of situate your free body diagram for each of them slightly differently. It's totally fine. So we tilted it for the mass on the incline, and we just left it as straight up and down for the hanging mass. And then we did our equations. We found that we had 2 equations. Well, we had 3 equations, but one of them didn't have anything we needed in it. So 2 relevant equations and 2 things we didn't know. So we just picked one of them and solved for one of the variables. And that was tension in this case. And then we plugged tension into the other equation so that we only had acceleration in the equation. We solved for acceleration. And then we plugged acceleration back into that tension equation and got the tension. So that is everything for today's lecture. I hope you have a great week.